Swayam Prabha. Digital India. Educated India.
So hi, welcome back. So we had started doing this example using several jets, right? And this was so this is something that we had drawn up of like 5 jets of different fluids, which have their different properties, right? And so we proceeded on this and we started to look at, we had to comment on U naught by Uj and R half, right? So jet half width and the velocity, right, as a measure of, as a fraction of the jet velocity. Okay, so these are the parameters which were given to us, and then so we did this, we found out the Reynolds numbers corresponding to each of them, and I think what's most important is that we found that the Reynolds numbers are quite sort of really quite different to each other. Number 1 and 5 are kind of close as such, but other than that they're all pretty far apart, and there's nothing much as far as the similarity as per Reynolds number is concerned. It's nothing similar, so these are all quite spread apart. Okay, all right, and so we did that, and we talked about, of course, the spreading rate and the slope of the curve, which is the velocity. One by slope of the curve being the velocity decay constant, which is B is essentially the velocity decay constant, and 1 by B is the slope of the curve. So we looked at, this is something that we had done earlier, so we were just sort of re-looking at it, and we had said basically that B is equal to 6 and S is equal to 0.14, which is this has been verified by experiments in literature. Okay, so we did this, and then we also looked at basically these are self-similar, right? And we looked at this plot in terms of zeta and eta and functions of those, right? And we came upon this, and finally we basically said that the mean velocity as a function of U naught, right, is essentially equal to half. So mean velocity at equal to half. So mean velocity at R half, right, is also equal to half. So this is something we did, and using that, now using these definitions, okay, these definitions, one was this, where we took B as 6, S is equal to 0.1, and we looked at these plots, and then we said that U mean, right, at R half, right, as a function of, or as a fraction of the center line velocity is equal to half, right. So having done that, so then we had stopped here. So we said we took the first case, and these are the values that we got, x naught by d to b. So x naught is given to us, d is specific to the jet, and we got that to be equal to 1. This is jet velocity, which is equal to 10, and then we got this value, which is, so let's just say, right, so then, so we're going to look at this. So U, if you see this formula here, so Uj by U naught, right, is equal to x minus x naught by d into 1 by b, right. So if I do that, so that's what we get here, right. So U naught, 10 Uj, that's the jet velocity, by U naught yeah, by x naught, x by d minus 1 is equal to 1 by b. So we put those values in, right? This is equal to 1 by b. So we get the value of b, which is again equal to 6. So what we end up actually is this relationship. Actually, we end up with this relationship. So for the first jet, the u mean, right, at the jet half width is actually equal to 7.5 by x minus 0.25, and we know that u mean is a function of x as well, right? So therefore this. So we then just took x for a particular value of x, which is say 1.25. We got the u mean at the r half, at the jet half width, to be equal to 7.5. So I think we had stopped here, and what we said is that you go ahead and calculate these things for practice, right, for the other 4. So what I will basically do now is to go and I'll go and sort of do it, make the calculations for the others, and you can cross check. Hopefully you've done this and you can cross check, and if I make a mistake, be sure to tell me. Okay, all right. So the second one, right, let's see if I go to the second one. So your x naught by t, right, in this case x naught is given, right, and the diameter is given to be this, right. Uj is 100, right, therefore 100 by u naught, right, by x by d, which is 0.05 minus 5, right, because it's x naught by d, right, is equal to 1 by b or 1 by 6, right. So, or I'll just say b. You can u naught, right, x minus 0.25 by 5, right. So this, right. Now then, okay, b is that, and mean velocity at r half is equal to u naught by 2, right. So in this case, u naught by 2 is half into, half into 5b by x minus 0.25, right. Okay, so this is equal to, how do you get 15? Okay, sorry, yeah. So then b is equal to 6, right? So this turns out to be 15 by x minus 0.5, right? So then essentially, so what we're saying is this. So then let's just say at x is equal to 1.25, okay, u mean x is 1.25 r half 0, right, is equal to 15, okay. Okay, so let's just right, this is that, okay. So okay, so u mean, right, at some x at r half is 15 by this, right, and so then I choose specific x is equal to 1.25 and the u mean becomes 15, right. So that is for the second case. Let's go and do this for the third one as well. Okay. Okay, here x naught by d is equal to, right, so this is equal to that. Okay, now uj is equal to 2, right. Therefore, what we can write is that 2 by u naught by x by d minus 0.5, right, is equal to 1 by b, or okay, b is equal to u naught into x minus 0.25. Okay, so then right, this is equal to 3 by x minus 0.25. Okay, because u mean, right, so we know that u mean is equal to u naught by 2, right. Okay, so using that we get this. So therefore, at x is equal to 1.25, u mean 1.25, r half is equal to 3. Okay. Okay, then so we got the third one down. Let's look at the fourth one. Okay, so x naught by d is equal to 0.25 by 0.15, which is equal to 5 by 3. Okay, then uj is equal to 25, right. Therefore, again, well, 25 by u naught by x by 0.15 minus 5 by 3, right, is equal to 1 by b, or b is equal to okay, that then u mean is equal to basically u naught by 2, right. So that is or u mean, so x r half is equal to okay, right. Then therefore, at x is equal to 1.25, u mean is equal to 75 into 0.15. This. Okay, so finally for the kerosene, so again x naught by d is okay, the jet velocity is 250, okay, then point 1 is equal to 1 by b. Okay, so then or u mean x r half this is equal to this. Okay, then therefore at x is equal to 1.25, u mean 1.25 r half 0 is equal to 75. So, okay, I think what you can see here that, so we've got all these values here. Why don't we sort of write this down, okay? So, we'll just tabulate that and see if we can make some sense out of it. So, this is something that we started out, like we said, you know, so we looked at, you know, several of these jets, right? And there is a specific x naught, which is 0.25, right? And we are looking at, you know, each jet has its own property. And then we are looking at the mean velocity at, say, x location 1.25 at the jet half width and see what we get, right? So, what we can say is that if I, this is something that we have. So, if you see this, right, so I have written down the Reynolds numbers here, okay. So, the water, air, castor oil, etc., etc. So, let us do one thing, let us go ahead and, so if I do this, okay, let us just say, let us just tabulate that, okay. I am going to write out the mean values, okay. So, then you have first one, and I am also going to write out the some of these values, okay. So, if I write this here, then for example, this is the jet, okay. So, this is a jet fluid, okay, and let us write out the Reynolds numbers. Let us write out the center line velocity, and now the mean velocity at 1.25 this location. Okay. So, 1 is water, 2 is air, castor oil, a fuel oil, kerosene. Okay, so the Reynolds numbers that we calculated for the water, it is 3 million. For air, it's 5.45. Castor oil is 1471. Okay, this, right? Let's look at what is U naught. Okay, center line velocities. Well, I guess we didn't calculate that. Let's just write down the mean values first, right? We can, okay. So let us write this down. So we can actually get, U naught is essentially 2 times U mean. So there's no point sort of writing that out, okay? All right, so U mean, we started out, the first one was 7.5. Okay, what's air? Air was 15, right? So this was the second one, which turned out to be 15. Okay, the third one was, 3. Well, is it? Yeah, 1.25. So let's just go back and let's see what did we get for the third one. Second, yeah, the third one is 3 actually. Okay, then the fourth one, what did we get? Fourth one is 75 into 0.15. It's slightly more than 7.5. Let's just put it that way. Okay. And 5 is 75. Okay, so these are a specific location. X is equal to 1.25 at the jet half width. Right, so this is the mean velocity, right? This is the mean velocity, and you can see here there is really no sort of pattern into this. However, if I were to this has the maximum RE. This has the fifth one, the kerosene has the maximum RE. Then you have the water. Then you have fuel oil. Then you have castor oil, and then you have air. Right. So what I can see is that it's decreasing, right? The Reynolds number is decreasing as I go from, say, so Reynolds number decreasing. So if I were to just write this, Reynolds number decreasing, first we have kerosene. Then we have water, then we have fuel oil, then we have castor oil, and finally air. Okay, so this is Reynolds number is decreasing, right? What's U mean? What is kerosene? Kerosene is 75, then water is 7.5, fuel oil is it is less than this, right? Then castor oil is 3, okay, and air is 15. Okay, so that is the mean velocity. So this is the Reynolds number, right? And you can see that I have calculated these for a specific location. Yeah, so this is one way of posing a problem, or with all the equations and all the understanding of jets that we have, what's the kind of information that we can extract? I think this problem is basically telling us that. Okay. Okay. So what is interesting is that the Reynolds number is of kerosene and water is at least I won't say, I guess it's comparable. If not comparable, at least they are sort of not too far off compared to the others. And you see that, however, when you go from kerosene to water, I think the U mean, the mean U, so this is this also, right? Now that decreases really sharply, right? It decreases sharply, and then of course it's not that much, right? So if you go from 1 million to the 3,000, around 3,000, and around 1,500 to about 5, single digit, okay, and we just kind of see that. So that's that. Basically, this is a problem where we had to, we're given numbers and we were trying to comment on this and that. Okay, so you can play around this with this a little more and see what more information you can gather. What are the things that you could plot or look at, which will give us some information. Okay. Okay, so I think having done that, okay, let's look at something which is pertaining to of course it's pertaining to the turbulent discussion that we are having, but I'll move away from the jets for a while, for a little bit, and really look sort of into a turbulent flow and see what's going on. And I think one of the things that at the first, when we were looking at the pictures and we were sort of trying to figure out what turbulence is and what does it mean physically, what does it mean? When I say there's a turbulent flow, what exactly does it mean? Does it have lots of swirling fluid in it, which technically you would call them vortices, right? Or do you have lots of them? Do you have big ones? Do you have small ones? We have all sorts of questions, right? And we tried to answer those. And Kolmogorov, I think, his hypothesis is what I think we concentrated on. So let us see an example, right? So given 2 RE, right, and okay, for a largest eddy scale, L naught is equal to 1 millimeters, right? Comment on the smallest scales, and effectiveness of dissipation. Right, with change in RE, based on hypothesis. Okay, so essentially what the question is that we have 2 given Reynolds numbers, right? Now we've spoken about this before, like the Kolmogorov's length scales, where we're talking about what's the size of an eddy, because there is the energy cascade. It is there are these eddies which contain the maximum energy, due to which there is random motion, and we have what we know as turbulence, right? And they look like blurred pictures and a lot of cloudy stuff, right? That's how we've seen it so far. Now the point is that how big is the biggest one, how small is the smallest one, and the point is, if there is a large eddy, right? So it does not remain large for the, like the whole time. So that the energy, it will break down, and the energy is going to get transferred, right, to the next one, right, to which one? To a smaller one, okay. So, and how long does this happen? Till it reaches an eddy size, till it reaches basically an equilibrium, right, where there is no exchange of energy between eddies, but the eddy has its own, eddy is small enough, it gets its own energy, and then there is a little excess in that which it dissipates. So that is the dissipation range of eddies, which it will basically decide where the transfer of energy is going to stop, right, and only dissipation is going to happen. So for the largest eddy scale, he has given you an L naught of 1 millimeter. So L naught is essentially the size of the largest eddy, right, 1 millimeters. So comment on the smallest scales. What will happen? Now let's just say we have a largest eddy scale which is of 1 millimeters. Then if I have two different Reynolds numbers, will the smallest scales of the eddy be different? Right, because there is a difference in Reynolds numbers, and effectiveness of dissipation with change in Reynolds number based on Kolmogorov's first hypothesis. Okay, so let's see, how we can approach this. Okay, now hopefully you remember. So in Kolmogorov's first hypothesis, we described length scale, velocity scale, and time scale using epsilon and coefficient of viscosity, right? We did that, and in that eta is essentially the length scale. Okay, now from Kolmogorov's hypothesis, okay, this Kolmogorov's first hypothesis. Okay, so, and like I said, it is a length scale. Okay, so then let us calculate. Okay, let us calculate and say then so if it is Re is equal to 10 to the power 4, right, then eta by L naught, okay, this, okay, or well, just give me a sec. That's not what. Okay, so is equal to Ra to the power minus 3 by 4, right? Then first case, ten to the power 4, right? Therefore, eta is equal to L naught into 10 to the power minus 3, right? And here L naught is given as 1 millimeters, or eta is equal to 0.001 millimeters. Okay, and again, right, eta by L0 is okay, this, therefore Okay, so essentially what we're saying is that the length scale, right, the length, Kolmogorov length, right, changes from 10 to the power minus 3 to 10 to the power minus 6 if we change the Reynolds number from 10 to the power 4 to 10 to the power 8. That's what we see, right? So if there is an increase, there is an increase in RE, right? Size of the, so there is an increase of RE here. Let's write that down. Okay. So what does this correspond to? So increase of RE, what does this correspond to? This results in what? The size of the smallest eddies decrease, right? So the size of the smallest eddies is 10 to the minus 6, right? As the Reynolds number has increased compared to 10 to the minus 3. Okay, so increase of RE corresponds to the size of the smallest eddies decrease compared to the size of the largest eddies. This, right? And so basically what we're saying is that if I increase the Reynolds number, right, the smallest eddy size becomes smaller, smallest eddy size becomes smaller, right? So that also decreases. So if I increase the RE is increasing, then the size of the smallest eddy also, if RE increases, size of the smallest eddy decreases. Let's put it that way, right? Okay, so then now let us remind ourselves a little bit about the dissipation range. Now if that is so, then the dissipation range is directly connected to the size of the smallest eddy, and hence that will also decrease with increase in RE. Okay, so let's just remind ourselves about the dissipation range. Okay, we've learnt all this stuff before, but let's just remind ourselves a little bit. So we had this. Okay. Okay, so let's just say this is eta, this is L of di, this is L of ei. Okay, this is this, right? Now L of di, okay, okay, and ei 1/6 of L naught, and L naught is actually comparable to, right? So L naught is the size of the largest eddy, right? And eta is the size of this eddy in the smallest eddy, okay? And L plus is actually the length scale of the turbulent length scale, complete length scale, okay? And right, so this was so this is the complete equilibrium range. Right, so this is the equilibrium range, okay, universal equilibrium range, and this is the dissipation range, This is the dissipation range, and this is the inertial subrange. Okay, and this of course is the energy containing zone. Okay, so this is the net equilibrium range. Okay, so which is essentially less than 1/6 of this. So in this context, as you can see that the net equilibrium range is less than 1/6 of the largest size of the eddy, right? Now, so in this case, our length scale has actually gone from from eta is equal to 10 to the power 3 millimeters to minus 6 millimeters. Okay, so and the Reynolds number is increased from right. So if the Reynolds number increases, the size of the smallest eddy, right, the size of the smallest eddy is decreasing. Right. Now you can see here, now this is the range that we are talking about. We are talking about this range, right. So let's just say eta and LDI, so therefore 60 eta or LDI, right, which is the cutoff for this thing. So LDI, right, is equal to point this, right, and L of DI. Okay, so this is when RE is, so RE is equal to 0.8, then okay, then this becomes much smaller, obviously, right. So it becomes something like okay. So this is essentially, so this is the range. Am I okay? Or this is right. Okay, millimeters. So as you can see here that LDI is shifting. So LDI is shifting. So this net equilibrium range, or where the dissipation range is essentially here, right? It is essentially here, and this LDI is shifting because of the change in Reynolds number, and it is shifting quite a bit, right? So the range is also affected. So you can see here that the dissipation range is directly connected right, is directly connected to, so the dissipation range is directly connected to the length, to eta, with the length scale, right, and this decreases, this also decreases, as we can see, right, with increase in RE. So essentially increase in RE, right. Now number A is the length characteristic length, I guess, but let's just say size. Okay, so size so the size of the smallest eddies, so the size of the smallest eddies decreases, right? And secondly, the dissipation range also decreases, right? So that is with the increase of Reynolds number. So okay, so I think we'll stop here, and we'll continue to do a couple of examples like this in the last phase of this classes, I guess. So we've got about 10 classes where we'll kind of do this kind of stuff. Okay, so that's it really. So and so basically, what the point here is that when you looked at the spreading rate and the velocity decay constant of a turbulent jet, that was independent of Reynolds number. It didn't matter, right? That was a turbulent jet, right? Now here you're going into the turbulence itself, right? You're looking at the turbulent properties of a fluid, right? And you see that if you come down to the smallest length scales, right? If you start looking at that, and then you see that this whole energy content and how that turbulent behavior is going to, because if you go into details, let's put it that way, right? So the mean velocity, when you compare that, when you compare the mean, when you are plotting mean velocity over central line velocity, and all of that, they are self similar, and we can see that they have a specific spreading rate that depends on the Reynolds, that depends on the jet halfway, that depends on the x, right, distance away from the jet and all of that. But not so that, right? However, none of these really it didn't matter. The Reynolds number does not affect the spreading rate, how the jet is spreading and how much is the spread. Reynolds number it doesn't depend on it. That was interesting. But now if we come here, right, and what was the problem? So we are basically saying that we have these things, but if you look inside, if you look into the details, and then you see that how many eddies are there, which is large, which is small, how much is being dissipated, how much energy is being dissipated, what are the energy containing zones. Now that, however, is dependent on the Reynolds number, right? And we see that if I increase the Reynolds number, then the size of the smallest eddies decreases. And if that happens, then the length range basically over which dissipation is going to happen also decreases. When I say length range means what? That's the length. So eddies whose sizes fall within that range will basically have energy dissipating from them, right? That's what it means. Okay, so we'll stop here and we'll take up another example in the next class. Okay, thank you.